Hello, everyone. Welcome to another UAA Professional Development Seminar Series. Today, our guest speaker, Chandler Kemp, will answer the question, is it time for an energy transition in the Alaska fishing fleet? Chandler is the owner of Kemp Energetic, a small business providing energy efficiency consulting services in Alaska. Chandler completed a Bachelor of Arts degree in physics with great distinction at Cornell University, worked as a research associate at the Alaska Center for Energy and Power, ASAP, and completed a Master of Science degree in Energy Resource Engineering at Stanford University. Thank you very much, Chandler, for accepting our invite, and we are very excited for your talk. Please take it away.
Thanks, Mohammed. So as Mohammed said, I'll be talking today about the potential for an energy transition in the Alaska fishing fleet, and specifically how we can start to introduce alternative energy into some vessels in specific circumstances in the fleet. So let me, next slide here. So, as Mohammed said, I studied physics at Cornell and energy resource engineering at Stanford. I'm originally from Haines, went to Haines High School, and I've been working with the Alaska Longline Fishermen's Association on energy efficiency projects since 2016. In addition to that work, I provide energy auditing and modeling services to clients and research energy efficiency opportunities. So before I launch into the meat of the presentation, I wanted to give a brief overview of what types of vessels are in the fishing fleet in Alaska. So in 2019, there were just about 9,000 vessels registered with the Commercial Fisheries Entry Commission. And if you look at the figure on the right there, it's a histogram with length on the x-axis and the percent of vessels in each bin on the y-axis. And so you can see the vast majority of vessels are between the 20 and 60 foot length categories. And if we broke this down further, you'd actually see that there aren't very many vessels in the 20 to 30 foot range. So it's mostly 30 to 60 feet. And so that's the class of vessel that we're going to be talking about today. I think it's also just to give a sense of the scale of fuel consumption that's involved in the fleet. I've worked with fishing vessels to do energy assessments where the owners reported consuming anywhere from 500 to 75,000 gallons of fuel per year. So fully 2 orders of magnitude range there. But I think a conservative estimate of what the average annual fuel consumption for a vessel would be around 2,000 gallons a year. And so with 9,000 vessels, that would give you about 18 million gallons of fuel consumed every year by the fleet. Maybe 10 to 50 million is a realistic range given the uncertainty around that annual fuel consumption estimate. And I also wanted to highlight that these vessels participate in a broad variety of fisheries, everything from hook and line fisheries to trawl net fisheries to gillnet fisheries to pot fisheries. And so, depending on what type of fishery the vessel participates in, their energy load profile is going to be very different. So for the rest of the presentation, I'm going to divide it into 3 sections. The first is going to go over measurements. So this is how can we characterize the energy loads on a fishing boat. The second section will describe the results of the measurement campaigns that I've been a part of. And so I'll try to quantify how energy is used in different fisheries. And then finally, I'll try to take those results and say, how can we use our measurements to inform investment in alternative energy systems? And are there places where we might be able to start to introduce an energy source other than diesel fuel into the fleet? So that's where we're headed. All right, so where does all the fuel go in a fishing boat? Well, the first thing we're going to measure is propulsion. So if we have every vessel in the Alaska fishing fleet is going to have a diesel engine that provides propulsion power. And to measure fuel consumption, I've gone onto these vessels and installed fuel flow meters on both the supply and return fuel lines. And that gives a real-time measure of fuel consumption. And I can also install a strain gauge on the propeller shaft. So I think there's probably some mechanical engineers in the audience here who know all about this, but just in case some of you don't, a strain gauge is something that you can glue to the shaft, and it actually measures how much the shaft twists when the propeller is turning. And if we know the material that the shaft is made out of and the diameter of the shaft, we can use that twist to then calculate the torque that's applied to the shaft. And we combine that with a measure of the rate of rotation of the shaft to get a direct measure of the power consumed by the propeller. So with these measurement devices installed, we can discover some interesting things. So this plot is showing data from a sea trial that I did on I believe this was a troll fishing vessel. So on the x-axis, we have the power measured with that strain gauge in horsepower. And on the y-axis, we have fuel consumption in gallons per hour. And I have two different data sets shown. The blue dots represent measurements taken on the vessel during sea trials, whereas the orange dots represent manufacturer data. And so you can see that the measurements are showing a little bit more fuel consumption than is expected based on the manufacturer's data. And there's a couple explanations for that. First of all, maybe the engine's not operating quite as efficiently as it was in laboratory testing by the manufacturer. And secondly, there may be some phantom loads on the engine that aren't captured by the strain gauge. So maybe there's a pulley driven, that's a pulley that has to be turned by the engine whenever it's on, and that's adding some additional load and increasing the fuel consumption. But there's two major takeaways that I want you to take from this slide. The first is you can really approximate the fuel consumption rate as a linear function of the load on the engine, and get a pretty reasonable estimate of the fuel consumption. And so I'll be using that property later in the talk. And the other thing I want you to notice is that even at zero load, there's non-zero fuel consumption. And that shouldn't be too surprising, because just to keep the engine running requires some power to run the fuel pump, and it requires overcoming the internal friction of the engine. And so even if there's no useful work being done, the engine is still going to consume fuel. And on the vessels I've been on, that's been around 0.3 to 0.5 gallons an hour in most cases. So now we can look at this same data differently, and to think about the efficiency of the engine. So in this plot, I have the fraction of the rated engine power on the x-axis. You'll notice it only goes up to 50%, because at the maximum engine RPM, that's all the power the propeller could consume. And on the y-axis, I have the brake-specific fuel consumption. So that's the gallons consumed per unit of energy. And here I've used the perhaps unusual units of horsepower hour. But the point of this slide is you can see that once you get down to below 10 or 5% of the rated engine load, the efficiency of the engine decreases quickly. And that's really because of that engine overhead fuel consumption becoming more and more significant. And so this property where the efficiency decreases rapidly at light engine load is something that will come up later in the presentation as well. So finally, if we combine that power measurement that we made with the strain gauge with a GPS that measures the speed over ground, we can look at how power is related to the speed that the vessel is transiting at. And the main takeaway I want to highlight here is that once you're below about 4 knots, 3 or 4 knots, the propulsion load is actually quite small. And it only increases rapidly as you approach the hull speed. I put hull speed in quotes because that concept is a bit more complicated than it's often presented as. But essentially, the hull speed is an estimate of when there will be constructive interference between a wave created by the bow of the vessel and the stern wave of the vessel. And so when there is constructive interference between those waves, the drag on the vessel increases rapidly with speed. So there's a few different curves here. These are from different sea trials on the same vessel. The blue curve is when the vessel has an empty hold and no gear deployed overboard. The green curve is when the vessel hold is full of water. And the orange curve is when there are stabilizers deployed overboard that the stabilizers are similar to a sea anchor. It's something you drag through the water that reduces the amount of rocking in the vessel in heavier seas. And so you can see that having stabilizers deployed increases the fuel consumption or increases the power required to achieve a particular speed. And it's especially significant at lower speeds. Well, it can be a large increase in the power requirements at any speed, really. Okay, so there's several other types of loads on the engine that I'll go through in less detail, just in the interest of time. So the next one is almost every fishing vessel is going to have hydraulic loads on the vessel. So these are things like that might reel in a fishing line or haul a net or set a crab pot. So the hydraulics are going to be typically powered by the main propulsion engine. And in order to measure the energy that they require, I've installed pressure sensors in the high pressure side of the hydraulic system. And we can combine that measured pressure with an estimate of flow based on the speed of the pump and the displacement of the pump to then get a measurement of the power consumed by the hydraulics. The next load class here is refrigeration. So many vessels use refrigeration systems to chill the fish once they're on board. And they can be powered in a variety of ways, sometimes with an auxiliary electric generator, sometimes with a mechanical coupling to an auxiliary engine, and sometimes even driven up through the hydraulic system. But in the example I'm showing here, we have an auxiliary electric generator, and we've installed an amp meter on the one of the leads to the compressor to measure how much energy it's consuming. And of course, we also need to measure the voltage and the power factor to get an accurate estimate of energy consumed there. Finally, every vessel is going to have an alternator. So this will be driven again by the propulsion engine, and it's used to charge batteries, supply hotel loads, perhaps even power an inverter that supplies 110 AC to electronics on board. And so again, with that, we can measure the voltage and log the amperage over time to determine how much energy is consumed by the electrical systems. So that's an overview of the type of energy consumption or energy loads that are on fishing vessels. We have propulsion, we have refrigeration, we have hydraulics, and we have electrical loads. So we combine measurements of these loads with measurements of the fuel consumption, and we can get an efficiency of the engine. And also use it to estimate how much we could reduce fuel consumption by considering alternative systems. So the data I'm going to show in the next section is based on work I've done with dozens of vessels in the last 4 years. So through the Longline Fishermen's Association, we've worked with vessels to conduct sea trials on 29 vessels. And so in those sea trials, we measure all the loads that I showed and go and operate the vessel at different speeds and measure the power requirements at those speeds. In addition to those sea trials, we completed surveys with 49 other operators about how they use their vessel. So how fast do they operate, or how fast do they go in transit when they're headed to the fishing grounds, or how many hours a day do they spend hauling gear? These types of questions. And then finally, I've also helped over 50 other vessels apply to the Rural Energy for America program. And so that program is available to fishermen that want to make improvements on their vessel that will reduce fuel consumption. And it requires a quantitative estimate of the impact on fuel consumption of the retrofits they're consuming. So this is the summary of the work that I've done to inform what energy loads are on fishing vessels. So I'll pause here briefly and see if there are any questions, but I think so I'll just give it a second here. And if not, I'll move on to the next section where I want to present results from these measurement campaigns that I just described.
Okay, so I've got a quick question. So, so you've just described the various different loads from propulsion to actually using kind of auxiliary power for other systems. When it comes to your research and what you've been looking at, does it make sense to try to separate those systems so that some of the auxiliary load, for instance, could, use solar or something like that, and the propulsion kind of remain the same if that has a profound impact or not?
Yeah, that's a good question. I think that regardless of where these loads are coming from, they're increasing fuel consumption from the engine. So if we think back to that sort of linear plot of fuel consumption as a function of load, whether you're increasing the load by turning on a light in the cabin or by increasing the speed of the vessel by 1/10 of a knot, either way, you're going to increase the fuel consumption rate of the engine by a similar amount. And so if we had, say, a solar panel on a boat, it would, and you could use that to take away part of the cabin load, or to potentially have some sort of motor that provides some of the power that's required for propulsion. And either way, it would reduce fuel consumption. But I think, practically speaking, it's probably easier to power a light than have an extra motor attached to the propeller. So perhaps there's some space for that. That being said, the key concept that's going to come up later is, when the engine's operating inefficiently is when it's lightly loaded, say during fishing hours. And so if you can find a way to turn that engine off while you're fishing, and supply the loads with an alternative system, that's when you get the most bang for your buck. And so that's really if we're looking at ways to sort of pick off part of the load on the engine and power it with an alternative system, choosing those times when the engine's lightly loaded and taking away the entire load is the most impactful step, rather than say, well, I think that's the most impactful way to go. So I hope that answers the question.
It totally answers the question. Have you taken a look at battery walls aboard vessels? I realize that that's maybe a silly question because they can be rather hazardous, right? But yeah, if you have something like a battery wall or a battery compartment that can really store a great deal of energy, then that would have a similar effect of being able to run things without the engine running.
Yeah, we have looked at that, and vessel owners are starting to make those investments. One vessel owner has made that investment in Sitka. His name's Fabian Gruder. But also in other countries, people are starting to make that type of investment. And so I think there's real potential there.
All right, thank you very much.
Great. So now I'm going to launch into a bit more detail about the different types of loads that we've measured and how significant they are in different fisheries. But to do that, I wanted to give a quick highlight of what some of these fisheries look like. So on the top left here, we have a gillnet vessel. So gillnet vessels are typically relatively small, less than 40 feet. And their operating profile consists of transiting out to the fishing grounds, setting a net behind them. So you can see in the picture, if you look closely, there's a big spool on the back of the boat. And so they set the net from that spool at a low speed, and then they just drift with the net, often with the engine idling, or maybe providing a small amount of tension on the net for some period of time, and then reel the net back in and pull fish out of the net as it comes. So it's a very low energy load while the vessel's fishing. Trawl vessels are a little bit bigger, maybe 40 feet, and they actually set fishing lines behind the boat, multiple lines, with hooks on them, and reel in the fish. And so when they're fishing, they're typically using propulsion to go a couple of knots, and they have hydraulics to pull the fishing lines in and out. A longline boat sets a long series of hooks along the bottom of the ocean, and then lets them sit for a day or two or three, and then reels the line back in. And so the picture here is of Linda Bacon and Kemp Barkow from the Longline Fishermen's Association, and they're just hauling in a halibut from their longline. And I wanted to highlight here, this is the trawl vessel and the longline vessel. They're actually the same vessel. but they participate in 2 different fisheries. And so that's pretty common for one boat to have multiple operating modes. And then down on the bottom left, I've got a picture of a seine vessel. So seine vessels tend to be larger, maybe 50 to 60 feet. And in that fishery, they will set a net behind the boat using a skiff, and the skiff will actually pull the net around in a big circle and close the net, and then they lift the entire net up onto the deck. And sometimes, sometimes they might actually, rather than closing the net immediately, they might drag it through the water for a little bit. And so when they're dragging that net, or when they're dragging it around to close it, either way, the propulsion power is much larger than it is in the other fisheries that I described. And in addition, the hydraulic load is also larger when they go to lift that heavy net full of fish up onto the deck. That power block can be consuming 25 kilowatts compared to just a couple kilowatts to reel in a gillnet or pull in a fishing line. And then finally, I've got a picture of a trawl vessel here. So it's confusing because troll and trawl sound similar, right? But the trawl vessel is very different. It's going to drag a large net behind the vessel through the water. And these vessels tend to be much larger, maybe over 100 feet, with much larger loads as well. And I've gotten to work indirectly with a couple of trawl vessels, but haven't had an opportunity to make measurements on them myself. So these are the types of boats to keep in mind as we go forward here. So this plot is showing the breakdown of fuel consumption required for different types of loads in 3 different fisheries. And the data are from results of the vessel energy analysis tool, which is an online tool that I helped the Longline Fishermen's Association develop, where a user can go online and enter a few characteristics about their operation, such as the length of their vessel, how fast they go in transit, and maybe what fraction of the time they spend in transit versus fishing. And then the tool will pull in the measurement data that we've made to develop an estimate of the amount of fuel consumption required for each load on the vessel. And so, to create this figure, I used average values that I've seen in the measurement campaign to generate sort of an example fishing vessel. And I want to emphasize that these profiles aren't representative of the fishing fleet, because each vessel is really unique in how they run their operation. But I think they are representative of a boat that could reasonably exist within the fleet. So I want to just highlight a few things here. First, the first thing that catches my eye when I look at this is that the seine boat uses a lot more fuel in general than the freeze or gillnet vessels. And that makes sense, because the seine boats are bigger and they often try to go faster. So they should consume more fuel. And of course, we see that the transit fuel is the largest fuel consumer on the vessel, followed by refrigeration. And this is something that was surprising to me when I first started doing this work. But often refrigeration is one of the largest loads on the vessel. And it's because these refrigeration systems often have a very high duty cycle. And so they might be running close to 24 hours a day, whereas the vessel might only be in transit for 20% of the time or 30% of the time that they're working. And so even if the refrigeration load is a smaller amount of power, the energy consumption can be disproportionately high because of the high duty cycle. So if we move on to the freeze troll vessel, this is fascinating because, first of all, we see that refrigeration here is actually about equal to the transit propulsion. And that's pretty common in freeze troll vessels. I think I forgot to say what a freeze troll vessel is before, but so troll vessels, these are where they're catching the fish with hooks. Many of them will maintain their fish hold at -40 degrees Fahrenheit, so that they can freeze the fish really quickly as soon as it comes on board. And so, of course, that takes quite a bit of energy to keep the hold that much colder than the surrounding atmosphere. And so that's what I mean by a freeze troll vessel, is a vessel that keeps their hold at those super low cold temperatures. Another interesting thing here is I have this category called engine, which is probably a confusing name, but it refers to that engine overhead fuel consumption that I was talking about. So it's just, if you take the total number of hours that the engine runs and multiply it by the amount of fuel that's consumed by the engine, if it runs that long with no load, this is the amount of fuel that you get. And so and it's actually, in this example, it's the largest fuel consumer in the simulation. That really highlights how much time the vessel spends in a lightly loaded condition. So the vast majority of the time on troll vessels is spent fishing at with trying to maintain a speed of about 2 knots with very small auxiliary loads on the engine. And so while it's fishing, the majority of the fuel consumption might actually be going to just keeping the engine running. So that's a really interesting highlight from that section. And then finally, if you look at the gillnet vessel, I'm saying that there's no refrigeration in this example, and so that category is not there. And again, we've got transit requiring the majority of the energy there. So there's some highlights of sort of how fuel consumption might break down in these different fisheries. Oops. And you can find out some more details about what goes into this model at the website, where the link is on the bottom of the slide there. Okay, so that previous slide was sort of simulated results. The data on this slide is measured from a troll vessel in action. So on the x-axis, we have time, and on the y-axis, we have the total load in kilowatts on the engine. Yeah, and so the black line here is the total, like, instantaneous recorded load during the day. And then the different solid blocks are the average load for 4 different load categories over 30-minute periods. And so the red is propulsion, the green is the freezer. So on this vessel, it was a blast freeze troll vessel. And so it has this freezer system running 24/7. And then the orange is deck hydraulics. So these are they're called gerties that pull the fishing line in and out. And the blue that you can barely see on the bottom is the DC electric load. And so there's a few takeaways here. The first is, right, you see this big peak in load at the beginning and end of the day. So that's when the vessel's in transit from where it anchors for the night and where it's actually fishing during the day. And so it's going relatively fast during those times, it has a high load. The second highlight here is at night, there's a relatively low, very little load while the vessel's at anchor. And in particular, you can imagine if we were, instead of looking at a freeze troll vessel, we looked at a vessel that didn't have a freezer system, the load would be essentially 0 at night. And then the next point I want to make here is, while the vessel's fishing, it has a relatively low load, but still higher than at night. And in this case, we're looking at something like 17 kilowatts or so during the fishing day, which is actually higher than most troll vessels. So there's a few reasons. First, the freezer system. So if we think about a troll vessel that doesn't have a freezer system, that would remove about 8 kilowatts of load throughout the day. Second, the hydraulics here are coming in around 4 kilowatts or so. But the actual work required to haul those lines in is significantly less than that. And so there's some opportunity for efficiency improvement there. And also you can see that the hydraulic load is pretty much continuous throughout the day. But in fact, on most days, unless the fishing is really good that day, there's going to be a lot of time when the hydraulics are pumping fluid, but the gerties aren't turning, the line's not actively being hauled in. And so if you could turn those hydraulics on and off effectively, you could save quite a bit of energy there as well. And then finally, propulsion. In this case, we're looking at maybe 9 kilowatts or so of propulsion power. But if we look at sea trials, to go 2 or 3 knots without deck gear only requires about 2 kilowatts of power for most troll vessels. If we add drag from having fishing gear in the water, and it might add another kilowatt or so. But we're still only looking at around 3 kilowatts in that case. But if you have stabilizers overboard, which this vessel likely did on this day, then that can double the propulsion load. And then if he's also working into a headwind or something like this, it could get you up to that 9 kilowatts. But the takeaway, the point I'm trying to make here is that in general, we have a load profile with very low energy at night, peaks in the morning and in the evening when you're transiting from anchor to fishing grounds, and then low load during the fishing grounds. And the load while fishing on a vessel that doesn't have a freezer system and isn't using stabilizers can be well under 5 kilowatts. So that's a summary of sort of what a fishing day might look like. And it's going to be similar if you're long lining, where you're still transiting in the morning, going very slowly while you're pulling gear, and then transiting back at night. And it's going to be similar for a gillnetter as well, where you transit in the morning and in the evening, and then very low load while you're fishing. So I'll pause again here to see if there's questions. I think we have about 15 minutes left for the last section where I really get into what an alternative energy system might look like on some of these boats. So I'll just give it another few seconds and see if there's a question, and then we'll move on. Okay, so I've described how there are many different types of fisheries, many different types of fishing boats, and it's really hard to say like what alternative energy system might work in the fleet generally. And when I posed this question at the beginning of the talk of, is it time for an energy transition in the fishing fleet? There's really not a simple answer. But what I do want to highlight is specific circumstances where you might be able to have a big impact by thinking about an alternative energy system. So I want to consider an example here that I would consider like a best case scenario. So I'm going to think about a gillnet vessel, and I'm going to say that they transit 2 hours from port to the fishing grounds, and then they fish 15 hours per day for 3 days, with a half-hour transit from where they're fishing to where they anchor for the night, and then they return back to port on the 3rd day, at the end of the 3rd day. And I'm going to say when they're in transit, they're consuming 53 kilowatts for the total load. So that's enough to go at 7 or 8 knots, depending on the vessel. And while they're fishing, I'm going to say that they have a really efficient operation. So they're only consuming 3 kilowatts while they're fishing. So if we do the math, that ends up being a total of 453 kilowatt hours for this 3-day fishing trip. So I really want to emphasize here that this is a best case scenario for battery power. So it's a short transit time, it's a short duration trip, and the load while fishing is very small. So it's a best case scenario, but it's also not unrealistic. So the operating profile is really similar to the Sunbeam, which is a gillnetter owned by Fabian Gruder in Sitka. And he's actually installed around a 70 kilowatt hour battery bank in his boat to try to start to introduce alternative energy into his operation. So first, with this load profile that we're imagining, let's think about what a fully battery electric system would look like. So we need 453 kilowatt hours of energy. That's without any safety margin, so bare minimum. And if the appropriate batteries for this would be like maybe a lithium iron phosphate battery could be a good fit, or similar chemistry, or there are a few other chemistries that I might consider. But the bottom line is these batteries are going to cost somewhere between $300 and $800 per kilowatt hour. You might get $300 per kilowatt hour if you're buying more or less directly from the manufacturer with very little support, and certainly nothing to marinize those batteries. And then $800 per kilowatt hour is the price that you might get for something like the battery pictured at the right, which is specifically manufactured by Torqeedo and BMW for use in electric boats. So if we have 453 kilowatt hours, we're talking about $140,000 to $360,000 in batteries to power a 3-day fishing trip. So that I would consider that infeasible for most fishermen, especially given that it's still not enough to have a fully electric vessel because there's no margin for for air there. There's no energy available if you happen to go out on a windy day. Another limiting factor for this type of system is the volume. So if we look at the volumetric energy density of, say, this deep blue battery on the right, you end up needing a total volume of around 150 cubic feet. That's like a cord of wood, if you can picture that, like 4 by 4 by 8. It's a little bit more, actually. And so if you can remember that picture of the gillnet I showed and try to imagine fitting a cord of wood inside the hull there, there's just really not space to fit that many batteries in the boat. So I think that's another reason that having a fully battery electric vessel is infeasible. Weight is potentially another issue. The weight of 450 kilowatt hours of batteries is going to be around 7,000 pounds. Many of these vessels are designed to be filled with water in the fish, or at least fill the fish hold with water, and that water often weighs more than 7,000 pounds. So the weight actually, I think, is not much of a limiting factor, but the volume and the cost does make a fully battery electric system infeasible.
So really, really quickly, the battery cost has quite a range there, right? Can you tell us a little bit about the differences between the cheaper costing batteries and the more expensive batteries? Is that just a matter of capacity, or is there something more to it?
Yeah, so there are many things that lead to that range. So I think that the biggest factor is the sort of support surrounding that battery. So the batteries have to come with their own battery management systems that make sure that when they're being charged, each cell is getting charged equally, and also like a controller that can provide the charging voltage and current, and so the level of sort of the amount of research or development that's gone into making those systems advanced is going to be much higher in the more expensive battery. So I think that's part of it. Another part of it is, I've talked with one person who managed to purchase batteries at that lower price point, that $300 per kilowatt hour, but he actually had a lot of trouble getting the system installed and running because there was no support available for actually making sure that the system was installed correctly and working. And so, if you purchase the more expensive batteries, these companies tend to have much stronger support for the products that they're selling. So that's part of it as well. Another factor is chemistry. So I actually forget what the Torqeedo battery chemistry is at the moment, but it is a different chemistry than the lithium ion batteries that I've seen available for lower prices, and so they claim to have or advertise greater cycle life. And then I think the final piece is sort of these 300, the lower end of that price range is batteries that are not made for the marine environment and aren't certified for the marine environment, whereas the higher end of the price range is batteries specifically designed for the marine environment, and they come with a greater guarantee of safety. So those are some of the factors that go into that range.
Thank you very much.
Yeah, so a full battery electric system, I would say not very practical in the fishing fleet at this time. And that's in contrast, and there's been a lot of interest, I think, in creating electric ferries and other marine electric vessels. And the key difference between a ferry and a fishing vessel is that the ferries have really well-defined routes, and most often they can charge much more frequently. So for example, the first electric ferry in the US provided service back and forth across a river. And so it could charge whenever it got back to the same side of the river. So it could get away with a very small battery capacity and charge and discharge very, very often, which allows for a smaller upfront investment and a shorter payback time if you can get cheap electricity to charge with. And so that's in contrast to a fishing boat that needs to be able to go out for days at a time, discharging slowly and charging infrequently. And so it's a really different economic scenario in that case. So now I want to shift to thinking about a hybrid system. So what I mean by that is a system where you have a diesel engine in series with an electric motor generator, where either the engine or the motor can provide power to the propeller. And I call it a motor generator because it needs to be able to either consume electricity from the battery system in order to provide power to the propeller, or consume mechanical torque from or mechanical power from the engine and push charge back into the battery. And then in addition to that, we want to be able to plug into shore power when you're at the dock. So this is the type of system I'm thinking of when I say a hybrid system. There's other types of hybrid systems, but I won't go into those now. So the main motivation for fishermen that are interested in this is they want to try to make their operation more sustainable. So the amount of fuel that they can save is a critical thing to think about. And they may also be interested in being able to have a quiet operation while they're fishing, and have a redundant propulsion source. But the primary thing that we're going to think about is fuel savings. So a hybrid drive system can save fuel in two ways. First, by bringing power from shore. So that's, you charge the batteries at shore. You can use that power when you're at sea, and that will displace fuel consumption. And then the second thing, though, is that if you can use the hybrid system to improve the efficiency of the engine operation. So I've got this plot on the left here. It's the same plot from earlier in the presentation, but I want to remind you of this inefficient operation when the engine's very lightly loaded. And then I want you to keep that in mind when you look at the second plot, which is the sort of imagined load profile for this example. And so in this load profile, you start off going into transit out to the fishing grounds. You're consuming about 50 kilowatts. But then once you're fishing, you're all the way down here at 3 kilowatts for 15 hours. And then you have a short 30-minute transit period back to where you want to anchor, and then zero load. You can turn the engine off, whether you have a hybrid system or not, when you're at anchor there. And then this cycle continues. And so you can imagine that when you're in this fishing zone, you're going to be in this really inefficient operating point for the engine. And so even if you didn't have shore power and you just charge the batteries with your engine while you're in transit, and then were able to turn your engine off while you're fishing, you could still save quite a bit of fuel, even without shore power. So these are the two ways that the hybrid drive system can save fuel. So this figure is looking at how you might actually use a battery in practice. So this is for a small battery, 20 kilowatt hours of power. I've assumed that you can charge it with a C factor of 1, so it takes 1 hour to charge. And so I've got the green curve is showing sort of the charge of the battery through time. As you can see, it's when you're in transit. Oh, sorry, and the blue curve in the background is a reminder of the load profile. Although I don't have an access to quantify it for you here. But if we look at the green, it starts off, there's no change in the charge, which means that you're using the engine directly, not the batteries, while you're in transit to the fishing grounds. And then you discharge the batteries and turn the engine off while you're fishing until the battery runs out of charge. And then you're going to have to turn the engine on for an hour to recharge the batteries, and then you can turn the engine back off again. And so that's the concept behind how the battery is being used in this application. The last critical point here is the battery is always being charged in this case when you're in transit. And so the engine's is loaded to an efficient operating point in that scenario. So it's a good time to charge the battery so that you don't have to run the engine at all while you're fishing. So that's the concept of how this type of system would be used. So now we can look at fuel consumption through time. So the orange is with a hybrid system, and the pink is without a hybrid system. And so if we start at time 0, and we look at the pink, we're consuming a lot of fuel to get out to the fishing grounds, and then while we're fishing, we're consuming relatively a lesser amount of fuel, and then it peaks again for each transit period. If we consider a case with the hybrid, it's the same in that first transit period because the battery's already charged at the dock. But then once you start fishing, you can turn the engine off, and you only have to turn it on for these short times to charge the batteries. At least that's the concept in this simulation. And then finally, when you're in transit, your fuel consumption increases beyond what it would normally be to provide extra power to charge the batteries. And there's a few efficiency factors included in here to try to make this realistic. So then so you can see sort of while you're charging, you're consuming more fuel, but then while you're fishing, you're generally consuming less fuel. In the end, if you add up all the fuel consumption, you end up consuming less fuel with the hybrid system, even after accounting for the inefficiencies of charging and discharging the batteries.
Is there a percentage that you can put on that?
Yeah, I think, is it the next? Yes, the next slide here starts to address that. So here I have battery capacity on the x-axis and fuel consumption for this 3-day trip on the y-axis. The pink line at the top is how much fuel I would estimate the vessel to consume without a hybrid system. And the orange curve is how much fuel I'd estimate the vessel to consume with a hybrid system, at the capacity that's indicated on the x-axis. So you can see the orange curve starts with a 20 kilowatt hour battery. So just what I was describing in the previous slide. And the fuel savings estimate there is around 30% of the fuel consumption for the trip. And then so that's due a little bit to the energy you're taking from shore, but mostly due to improving the efficiency of the engine operation, avoiding all that time when the engine is very lightly loaded. And then as you increase the battery capacity further, you continue to decrease the amount of fuel that's required. So I think that should be intuitive. The more electricity, the more fuel you're able to displace. And then the final little point here is if you zoom in at the beginning of this curve, as you're increasing the battery capacity up until you have enough to get through 1 day of fishing, you get a slightly more bang for your buck during that period than you do once you already have that first day of fishing covered and you're just displacing additional fuel with electricity here. So that this figure is sort of is summarizing how investing in battery capacity gives you a return in fuel savings. And I want to, if you do I have done the math to think through sort of what the payback period is for this, and it's not great. It's I don't actually remember, but it's a few decades, and so I wouldn't suggest doing this if you're trying to save money. But nonetheless, fishermen are interested in doing it to make their operation more sustainable, and also if they're really value having a quieter work environment during the day. Let's see. So I think I want to wrap up here so that to make sure there's time for questions. But I wanted to mention that there's a variety of other technologies that we can consider that I haven't gone into today. Even I think Andrew mentioned solar panels in one of the earlier questions, and that's not even covered on this slide, but it's something to think about as well. I would say the sort of surface area that's available on a boat it's going to be hard to capture enough solar energy to make a very significant impact on the total fuel consumption. But it's I don't want to dismiss that idea out of hand either. I think there's potential for it to have a role to play. So the few next steps I'm working on, including some work with Mohammed. So first of all, we're launching some measurement campaigns on trawl and longline vessels this spring and those vessels are hoping to install hybrid systems next winter. And so we'll measure the fuel consumption over the season this year, and then measure it again sort of once they've installed the hybrid systems, and hope to sort of validate some of the modeling results. We're also working toward doing some real-time hardware in the loop testing and simulation of marine microgrids. So we want to, similar to the way that a microgrid in a isolated community might be tested for robustness to faults. We want to do similar testing to vessels as they rely more and more on electrical power. And then finally, I do want to look into the feasibility of alternative technologies besides batteries. And this is, so I haven't done that much, but I'm interested in investigating biofuel and hydrogen and a few other technologies as well. So to answer the question from the title here, is it time for an energy transition in the fishing fleet? Well, it's not time to go to a fully battery electric fishing fleet, but we can start to introduce alternative energy to the fleet by thinking about hybrid propulsion systems. And so with that, I think I'll stop and see if there are any questions here.
Yeah, indeed. We do have a question from chat. It says, have you considered and modeled adding renewable hydro, solar, and/or wind in addition to the hybrid system? Now, I feel like you kind of covered that, but I wanted to ask the question anyway.
Yeah, great. So I think the question was how I considered adding hydro, solar, or wind, as part of the system in addition or to hybrid systems. And right, so I briefly mentioned solar and alluded to thinking that the amount of energy that you can capture while you're fishing is going to be hard to have a big impact on fuel consumption. For hydro, I think that's really a lot of the reason that any sort of energy storage system on the boat could make sense, because many of the fishing communities in Alaska, like Sitka or Juneau or Haines or Kodiak, have hydroelectric power installed on shore, and so there's a relatively affordable source of electricity available. Although, of course, we need to think about if there were a large-scale transition in the fleet, how that additional load would affect the community's electrical grid. And then finally, for wind, I think wind can have a great role. The best way to use wind in a fishing vessel is with sails. And so, I think if people were...
I was thinking about a solar sail, honestly. I was like imagining like, oh, that would be cool if you could somehow catch the energy from light at the same time as harnessing the wind on a sail, right? Because that would be the biggest area that you could really capture light on.
Yeah. I haven't really thought about that, but it's a fun idea.
All right. So yeah, if you could go back a few slides to the various different engines. There you go. That's the one. So yeah, I was thinking kind of about the Chevy Volt because I'm about that, and it looks like that's kind of captured in G. I think is that concept. I don't think that there'd really be a good way to get away from the engine entirely for propulsion, but is it feasible that you would have an electric motor, essentially something that like you would use diesel to recharge, kind of like in your hybrid model, but you would never use the engine for propulsion? It would always be run from battery.
Yeah, so I would point to E here as really that example. And so the system that I described is called a series hybrid because the propulsion engine and the motor are in series, I suppose. Oh, sorry, wait. I should say that's a parallel system because the engine can provide propulsion or the motor can provide propulsion. You have two like fully independent sources of propulsion power. Whereas E here is more of a series hybrid where you can either power the motor from batteries or from a diesel genset. But in either case, the motor has to provide all the propulsion power. There's no direct coupling between the engine. There's no mechanical coupling between the engine and the propeller. And so there's some advantages and disadvantages to both. So the parallel system that I described, where there is a mechanical coupling between the propeller and the engine, has an advantage in that when you're in transit, you can drive the propeller very efficiently because there's no energy transformations required between the engine and the propeller. So what I mean by that is, if we think about case E, in order for the engine to power the propeller, we have to, first the engine creates mechanical rotation of the shaft. That drives an electric motor, or that drives a generator, which creates electricity. And then we provide the electricity to the motor, which then converts it back into mechanical energy. And so there's a few efficiency factors there that are going to increase fuel consumption. Whereas with the parallel system, you have the engine creating mechanical rotation, and that drives the propeller directly, so a bit more efficient. That being said, if we have a marine propulsion engine, they tend to be big and bulky, and it needs to, and if you're running it in that way, it needs to have enough power to fully supply the load that you want while you're in propulsion or while you're in transit. But if we have this sort of series hybrid case, and if we think more of the genset as more of a range extender, so if you have, say, enough batteries that most of the time you're just running off batteries exclusively, and then you just have to use the genset occasionally as basically like a safety factor, then that efficiency loss while you're in transit is less important, and you might be able to save a lot of space by having a smaller genset. So I think that answers the question.
It totally does. Thank you.
Thank you very much, Chandler, for the great presentation. I really enjoyed the presentation and I learned a lot. I have a quick question. So what do you think can be done on the shore power system side to help with moving, with more fleet move to battery electric systems? So I think you kind of answered that question, but I thought maybe you could give us more detail. Like, what is the extra burden that the charging the batteries could be for the shore microgrids and shore power systems?
Yeah. So the good news is, in some of the larger harbors, there's already 30 or 50 amp 240 volt power available at many of the stalls. And so with that much power, you can charge, it's kind of like a level 2 charger for an electric vehicle. So there's reasonable charging capacity there. And the second piece of good news is, if we think about a few boats, well, in the example I just showed, it's like 450 kilowatt hours for a 3-day trip. That's a pretty small impact on a grid the size of, say, Sitka, Alaska, which is not a big town. It's 9,000 people. And so if there's just a few boats doing this, it's a pretty small impact on the grid, and there's already enough power available at some of the stalls in the harbor to have reasonable charging times. That being said, if we want to think about a larger scale transition in the fleet, many of these communities are already close to the capacity that's available from their hydroelectric systems. And so making sure that there's capacity available to make this transition could be important. I want to be careful saying that, because I want to acknowledge that developing new capacity has its own often negative impacts that need to be weighed against the benefits of how having additional electricity could be displacing diesel fuel. So that's one potential thing that communities could do to help support this, is ensuring that there's capacity available. And then the second thing is providing resources for vessels to charge even more quickly, or providing the existing 30 and 50 amp service to more stalls would also probably help some vessels to make these systems easier for them to charge these systems when they're in port.
Thank you very much.
All right. Well, it looks like that's all the questions that we had for today. For everyone who is seeking the survey password is phishing, all lowercase. And yep, looks like that's all the questions we had.
All right. Well, thank you for the opportunity to share this.
All right, with that, I would like to thank you again, Chandler, for the great presentation, and those of you who joined the seminar. Have a great rest of your day.